All right, so worksheet from yesterday. First question was, draw a sketch of a trough approaching a fixed end, then a second sketch showing that wave after it has reflected off that fixed end. All right, so there's a trough. There's my fixed end. Whenever we're drawing a wave, we should always indicate the direction of travel with a small arrow underneath. Okay, that's the before picture. This would be the after picture. Now I have a crest going the other way. Simple as that. It's going to reflect off the fixed end, inverted, and become the opposite. Okay, I still haven't looked at it.
Yeah, but if the question says fixed end,
yeah,
we assume that it's a more dense medium that it's going into.
A fixed end is an infinitely dense medium. It cannot travel into it. Is what we say, theoretically, right? Like it's obviously not. Basically, all of the energy, wave energy, is going to reflect off. There'll be, a slight vibration of, if it's like a hook into a concrete wall. Certainly, some vibration and energy will go into the wall, but nothing significant. A wave crashing into a cliff, same thing. Sure, some wave energy is going into the cliff. If I have a seismometer there, I'll feel it, but other than that, the wave reflects off completely. All right, questions on the first one? Okay, draw 3 sketches showing waves before, during, and after complete destructive interference. All right, if they're going to be destructive, I need one wave that is up and one wave that is down. Right, so this would be the before picture. This would be the during picture. And then this would be the after picture. Okay, indicating that the waves are traveling in the same direction they traveled before the interference and are essentially unaffected. Okay. Questions on that one? Right, for number 3, for this sketch, is the wave moving from a fast medium into a slow one or a slow to a fast? Fast to slow. How do we know? Yeah, the wavelength decreased significantly. And it also has what kind of a reflection? It has an inverted reflection. There's 2 reasons we know it's going into that medium and that medium is slower. Okay, we have a shorter wavelength wave and we have an inverted reflection. Those are the 2 indicators that tell us that. Okay, I always have a question like this on the unit exam. There's a multiple choice item, but it has 3 different media. Okay, so you have to go which ones like, is it low, high, low, high, whatever it is. Yeah, you got to figure it out based on the reflected pulses, okay, and things like that. So mostly the reflected pulses in that question. All right, so in this one here, we have a slinky attached to a string. Okay, the spring is attached to a light thread, which is a less dense medium, okay, and that thread is tied to the wall. What happens when the pulse reaches A? All right, what happens anytime a wave goes from one medium to another? It'll stay upright. That was actually not one of the things I was thinking of, but you're absolutely right, it will. Its speed will change, its wavelength will change. Actually, these are all great answers, and none of them are the ones I was thinking of, but they're great answers. Yeah, its frequency will remain the same. Okay.
It will change direction.
Well, actually, this pulse won't change direction. It'll keep going here, right? What I was actually thinking of, some of it will be reflected and some of it will be transmitted. But all those other things you guys said are true as well. They were like way more detailed answers than I was thinking or anticipating. Okay, this is mostly checking what happens to a wave at a boundary. Some's transmitted, some's reflected. At any boundary, that is true. And then yes, after that, okay, the frequency won't change, the wavelength will change, the speed will change. If this was oblique, the angle or direction would change. Okay, and we'll get what kind of a reflection are we going to get? From this to this?
Oh no, it would still stay the same.
Yeah, it'll stay upright. This is a less dense medium, so a reflection off of that boundary will be upright. And they'll be very small, practically unnoticeable, but it will be there. Okay. All right, what happens when the transmitted pulse, that is the one that goes from the spring into the thread, gets to B? It'll get reflected, yes. B is a fixed end. That reflection will be upright or inverted? Inverted, it's a fixed end. The reflection off a fixed end is always inverted. Okay? All right, everybody okay with that? All right, those were good answers. Okay, a long spring runs across the floor of a room and out the door. A pulse is sent along the spring. A few seconds later, an inverted pulse returns. Is the spring attached to the wall or lying loose on the floor? It's attached to the wall. Okay, if it was lying loose on the floor, an upright pulse would have returned because air is a less dense medium than the spring. All right. If I want to increase the wavelength of waves on a rope or a slinky, what do I do with the frequency? Higher or lower? I want to make the waves longer, so I would use a lower frequency because then it takes me longer to make the waves will be longer. Okay? If I use a higher frequency, I'll make lots of little short waves. If I use a lower frequency, I'll make longer waves. Okay. All right, similar situation to the other question. Now we've got a light rope and a thick rope, so a less dense to a more dense medium. Okay, what happens when the pulse reaches A? Some will be reflected, some will be transmitted. Okay, is the pulse reflected from A upright or inverted? Upright. Okay. Sorry, no, inverted. Sorry, it'll be inverted. It's more dense. It's going from less dense to more dense. The reflection from A will be inverted because this is a more dense medium. The transmitted pulse will still be upright, but the reflection will be inverted off of that bound. Okay? What happens when it reaches B? It'll reflect and it'll reflect inverted. Right? So there's two inverted reflections in this situation because we're going from less dense to more dense and from more dense to infinitely dense. Okay, so we'll get two inverted reflections. Right? So a little while later, what is this setup going to look like? This is going to be hard to draw. That's my knot. I'm not that good. Okay. That's what I'm going to see a little while later. Okay. This is the pulse that reflected off of here. This is the pulse that reflected off of there. Okay. Could get a question like that even in a written response. Say draw a picture. Probably. Usually when I ask you to draw pictures, it's pretty easy though, because you might have artistic ability like me. Karen. Okay. What property of waves never changes? Frequency. God help you if you get that wrong. Okay? Because I've said that so many times in the last week. Okay? Frequency never changes. All right. In this diagram, we're talking about interference. We have two wave patterns that are occupying the same space at the same time. Okay? Draw the waveform that would result when these waves interfere with each other. Okay. First thing we got to ask, are these waves in phase? They are. When one is up, the other is up. What kind of interference will that be? Okay. What do I do when I want to draw what this should look like? I add the amplitudes. 2 plus 4 is? Now, this may not be perfect for all of these points, but it's generally what I would be looking for. Okay? I wouldn't, look for much more than that. This is the general shape. You've identified it as constructive interference, and you show me that you know to add the amplitudes together. You're good.
On a test, do you want us to go point by point?
No, that's what I was just saying. This would be good enough. Okay? If you draw that along with this, full marks. Okay. All right. For number 10. What kind of interference is occurring at the named points? Okay, so at point G, that'd be right there. What kind of interference is going on? Constructive. They both have a positive amplitude at that location. At I, destructive. Yeah. Okay, they're opposite. One is negative, one is positive. K, destructive, and O, destructive. Okay. Pretty easy stuff. These are the kind of things you're going to get in the multiple choice, and to an extent the written response of the exam. All right, our two speaker question. Okay, everyone's done this question? All right, so our givens for this question are that we know the frequency of the sound to be 400 hertz. Okay, the speed of the sound is 340 meters per second. Okay, and they are standing 6.8 meters directly in front of one of the speakers. And the speakers are 6.42 meters apart. So that's my situation. If I want to determine whether the person hears a loud or quiet sound, well, let's see, what determines that first off?
The difference of the wavelengths number once they reach the person.
Right, the difference in the number of wavelengths traveled from each source to the observer. Okay, that's what will determine whether they hear a loud or quiet sound. If that is a whole number, 1 full wavelength, 3 full wavelengths, 100 full wavelengths, okay, then they're going to experience a loud sound because of what kind of interference? Construction. Okay, and if they have a half a wavelength out, so it's 1.5, 5.5, 10.5, then it's going to be destructive because they'll be meeting crest to trough. Okay, all right. So if I'm going to figure out the number of wavelengths from each source to the observer, there are two things I have to calculate right now. Wavelength. Okay, so to calculate wavelength, I would use the universal wave equation, manipulated it like so. 340 over 400. What does that come out to? 0.85. Okay, so my wavelength is 0.85 meters, and then I've got to do a Pythagorean theorem calculation, okay, with those two sides. So that will be the square root of 6.8 squared plus 6.42 squared. Okay, so we're looking at that side being 9.35 meters long. I'm going to keep all my decimals there. Okay. So I'd have given you a mark for givens, I'd have given you a mark for your Pythagorean theorem, I would have given you a mark for your wavelength. What do you have to do now? Before I can subtract, I have to get the thing I need to subtract first. I have to divide the distance by the wavelength in order to get the number of wavelengths from each speaker, because I've got two things that are in meters, meters per wave and meters. So I just need to get waves. Okay, so I'm going to take my 9.35 and divide it by 0.85. Was it exactly 0.85? Okay. All right, so we'll take that number there and divide it by 0.85. All right, so that's giving me 11. That's close enough to 11. Okay, yeah, because this never works out perfect. In fact, it takes a long time for me to get it perfect. Okay. So it's 11 wavelengths from this speaker. Okay, and then from this speaker, same calculation, 6.8 divided by, not times, divided by 0.85, 8. Okay, so I would have probably given you a mark for that calculation there. Okay, and then the last one is 3 wavelengths, loud. Right? It's a full number of wavelengths difference in travel, so they're going to be meeting at the same point in the wave. We'll get constructive interference, and the person will hear a loud sound at that position. Okay? Everybody good with that one? Did I tell you there'd be one like that on the test? Because there'll be one like that on the test. Okay. Any questions on any of those? So this whole idea of interference and wave behavior and stuff like that, it's important that we cover it now because the next thing we're going to talk about is standing waves. Okay? And standing waves are interference patterns that result from interference, okay, wavelength, frequency, wave behavior, reflections, okay, all of that kind of stuff. That all has to do with how these patterns stand up, and standing wave patterns are responsible for how musical instruments work. Okay, if you have a string instrument and you pluck the string, you are putting a standing wave pattern on that string. Okay, depending on where you pinch it against the bridge. Is that the right one? That's fretboard. Okay, wherever you pinch it against, you're changing the wavelength. By changing the wavelength, you're going to make that thing make a different frequency. You're going to make that string make a different frequency of sound because the speed is going to be the same. Okay? Now, can you change the speed at which the string vibrates? How? You turn the little cranky things at the top of the fretboard. They're little knobs. They increase the tension in the string. Tuning
knob.
Tuning knob. Okay, see, I knew they had a technical name. Cranky things. Okay. That's it. The only instrument I can play is like the music on my phone. I have no musical ability. So yeah, you turn that and you change the tension in the string. That changes the properties of the medium, which changes the speed at which the waves can travel. That's why if you pluck it and then crank on one of those tuning knobs, okay, you will hear it make a different frequency of sound. Okay, because you're changing the speed at which the waves can travel. That changes their wavelength and their frequency. Okay, or sorry, not their wavelength, changes their frequency because it's now making different waves. Everybody all right with that idea? Okay, what if you have a wind instrument?
Certain parts of it vibrate to make that sound?
Yeah, certain parts of any wind instrument vibrate, even if it's the lips of the person playing it. So if it's like a brass instrument, okay, you would have just the lips vibrating. And then what sets up inside the wind instruments is a vibrating column of air. Okay, so some part vibrates and causes the air around it to also vibrate and resonate and amplify and make the sound louder. Okay, because obviously what comes out of a trumpet or a trombone or a tuba is a lot louder than the sound that caused it. I'll turn away when I do it. That sound. Okay, I can't do it very well because obviously I don't play any instruments, but you do it much better if you do. Okay, but that's what happens. If you have an instrument that has a reed, okay, it's the reed that vibrates. Okay, or if you have a very simple instrument, simply blowing across the top of it can make it vibrate. Okay, I think a flute works that way, right? I think the flute doesn't have a reed, right? Okay, so it would do that. Or if you have a water bottle, okay, that you can blow across the top of, and I can't even do that. See, that's how musically not talented I am. I can't even play the water bottle. Okay. But if you had like a a jug, okay, or something like that, so you can blow across the top of, okay, then you can make the column of air inside resonate, vibrate. Okay. It's even simple to do that with wine glass. There's an instrument I can play. Okay, if you have a crystal wine glass and you go around the rim with your finger, okay, you'll get the crystal to vibrate, which will cause the air inside the glass to resonate. Okay, a standing wave pattern will get formed in there, and you'll get a musical note. If you drink some of the liquid, does the musical note change? Why?
Because more air is squeezed.
You're right.
Oh, okay.
Yes, the length of the air column changes. Because if it's half full with liquid, the air column is only this long. If you drink it all, the air column is now this long. It changes the wavelength, and thus it'll make a different frequency of sound. Okay, everyone follow me on that? That's how all musical instruments work. I can't play any of them, but I understand how they generally work because I'm a physics guy. Okay? So yeah, any of the string instruments, it's the nature of the string. That's why string instruments generally have more than one string on them, because you need a wider range of sounds that you can play. Okay, a piano has like tons of them. Every single key has one. So things like that. All right, is that making some sense there, Rick? Okay. If you're like playing your, let's say, string instrument, your guitar, in a room where the temperature is 10 degrees Celsius, and then you go, I don't know why you'd be doing that, but let's say you were, okay, and then you go and play that same instrument in a room where the air temperature is 25, is it going to sound the same? Okay, it's going to sound different. That's why instruments have to be tuned every single time you go somewhere. Okay, the air pressure is different, the air temperature is different. Okay, all of those things can affect the speed of sound in the air, and as a result, you would have to tune the instrument each time you go somewhere new. Okay, to account for the fact that because the speed is different, people are going to perceive the waves different. Making sense? It's not just for fun. Okay, you have to tune it every single time. All right. Okay, let's look at that first. Okay, so standing waves can be good if we're using, like a musical instrument or something like that. Okay, obviously we want a standing wave pattern to be formed. Standing waves can also be bad. Where would they be bad? Where would I not want standing waves to set up? Oh, sorry, I should introduce. Standing waves occur because waves are being produced and they're interfering and occupying the same space as their own reflections. Okay, so let me demonstrate. Easier. Okay, so standing wave patterns are the result of repeating patterns of interference. All the waves I put into that medium are exactly the same. So they always interfere in the same places. Okay? It's not that a standing wave actually stands still. The pattern stands still because there's waves constantly going back and forth, and there's areas of constructive interference and areas of destructive interference. Everybody with me on that? So it's the same for musical instruments, okay? It's the same for anything that makes a standing wave. Now, where would I not want something like that to happen? Upridge. Okay? Why would it be bad? Well, I mean, all bridges sway. Okay, suspension bridges sway. They're designed to. Okay? They have to. So they're designed to sway a little bit. What about a building? They move. Yeah. Okay. If you doubt it, go to the top of one of the buildings in downtown Calgary when we're having an 80 kilometer or an hour wind or higher. Like, people have to go home sometimes because they get seasick in their office. Okay? If they're especially sensitive. I'm not saying like people will be walking around the office trying to keep their balance, but it's enough that if you're really sensitive to motion, okay, that you can detect it. It can make you nauseous. Okay? But buildings are designed to sway ever so slightly. What they don't want is for that sway to reflect off the bottom, go to the top, reflect off the top, and come back. Because if it starts doing that, and the wind keeps blowing, you'll start getting a standing wave in the building, which means there'll be areas of constructive interference, areas of destructive interference, and then just destruction. Okay? It'll come apart. Right? So we don't want standing waves, obviously, to form in structures because of the interference pattern, okay? And the fact that there'll be increased amplitude. So what we do is we dampen them. Okay? We make one side of the building or one side of the suspension bridge have a different tension than the other side. Changing the tension in the two sides means that waves on either side don't travel at the same speed. Since they can't travel at the same speed, they can never set up a standing wave pattern. Okay? So you'll never get this problem. Right? Something that people didn't realize when they built the Tacoma Narrows Bridge. They rebuilt the bridge. Before they figured out why the first one went down. They just built it stronger. And 52 years later, they go, oh, here's this computer model that explains why that one went down. Okay. But it's been safe. It's built better, it's got better dampening, and that's the big thing. You keep a standing wave pattern from forming by dampening the bridge and making sure that waves cannot travel at the same speed on both sides. And that's true with any structure. And they do that with buildings and bridges in earthquake-prone areas as well. Right? If you have a sustained earthquake, you can get a wave traveling through a structure, okay, and get the same type of problem happening. So the footings that they put on buildings in earthquake-prone areas basically have like almost like a giant spring. It's not exactly a giant spring, it's effectively the same thing. Okay? And so when the building starts to shake and oscillate, it's dampened so that the sides can't do the same thing at the same time. All right, so standing waves result from patterns, repeating patterns of interference. Okay, those patterns are formed because you've got reflected waves as well as newly produced waves occupying the same place in the medium at the same time. Okay, and we're going to look at the proper names for the areas of destructive and constructive interference. All right, so a standing wave, like these ones here, these are the same ones that Emmanuel and myself produced on the spring. Okay, are simple standing wave patterns. Okay? The first wave pattern that you get on any medium is known as the fundamental. Okay? The fundamental frequency, or F1. Okay? The next one is known as, or this is also sometimes called the first harmonic frequency. This one would be the second harmonic. This one would be the third harmonic. Okay? Oh. Boy, I just need to start that one over again. Okay, so this is F3, this is F2. Okay, and as we saw, to make those patterns, okay, it's a multiple of the first one. So I had F1 where it was like 2 hertz, and then there was F2 that was 4 hertz, and then F3 was 6 hertz. Okay, they're always a multiple of the fundamental or first harmonic frequency. Okay. Now, can you get a guitar string to do this? A guitar string only does this. The way you change a guitar string, the frequency a guitar string makes, is you pinch it further down the fretboard, okay, so that only this much of it can vibrate. Then you would get this frequency. Okay, that's why you change your hand position on the fretboard. Okay, getting a standing wave other than the fundamental frequency is not impossible, but it would look ridiculous. Okay, on a guitar, you never see a string instrument string do all the way along. Okay, you pull it out and let it go, and it just vibrates at its fundamental frequency. All right, everybody okay with that? With a wind instrument, you simply change the length of the column of air that can resonate. Okay, and you do that with the keys, buttons, keys, okay, knobs, valves. Valves is good because that's, you let air out a different spot. Okay, if you're letting air out a different spot, you're changing the length of the air column that can resonate, okay, and that's going to change the frequency of the sound that instrument produces. All right, so in this figure here, we've got our standing wave pattern viewed from above. It's just a person who's going back and forth with a spring. Okay, this would be our fundamental frequency. The areas of constructive interference are called antinodes. The areas of destructive interference are called nodes. Okay, so a node is an area that does not appear to vibrate or move at all, okay, because it is an area of destructive interference. Okay, and then antinodes are places of maximum vibration, okay, and they are areas of constructive interference. Okay, now if you're looking at this diagram, don't worry about this. We don't use this terminology because we find it confusing, Okay? We use first harmonic, second harmonic, third harmonic, fourth harmonic, so that the number fourth, third, second corresponds to the frequency number, F1, F2, F3, okay? Rather than using fundamental and then first overtone. First overtone is F2, and people get lost in it because the numbers don't match, so we don't use that terminology, okay? This would be F2, this would be F1, this would be F3, and F4. Not F11, 4. There we go. Okay? Everybody all right with that? Okay, so each standing wave pattern is produced at a unique frequency. Okay, when Emmanuel and I were shaking the spring, okay, notice that neither of us moved. Okay, if I moved or he moved, we would have changed the tension in the spring, which would have changed the speed at which the waves traveled, which meant we'd have lost the pattern. Okay, in fact, you could see that when I was trying to get the 3-wave pattern, even the 2-wave pattern, it was taking me a little bit of time to find the frequency that made it, right? I was shaking it, it was just kind of a jumbled mess, and then I kind of found it, okay? Not all frequencies make those standing wave patterns, okay? There are particular frequencies that make those standing wave patterns, right? And if we change or alter any property of the medium, the frequency at which it vibrates in those patterns will also change. All right with that idea as well? Okay, so this is, again, our first harmonic, okay, our second harmonic, okay, our third harmonic, and so on. Now here's something that will oftentimes come up as a question. If this distance here is 2 meters, what's the wavelength? I heard somebody whisper it. 4 meters. Okay, remember, one full wavelength has a complete oscillation. Does that have a complete oscillation? It does not. Okay? This is only 1/2 of a wavelength here. So the full wavelength is 4 meters. Now, what's the wavelength of that? That one's 2 meters. Okay? So if there's one full wavelength here, how many wavelengths are here? 1.5. Yeah. Okay, 4/3. Yeah. Okay, and how many wavelengths are here? 2. Okay, it's important to be able to look at a standing wave pattern and identify there are this many wavelengths present on that or in that standing wave pattern, because then you can determine the wavelength because you would know the length of the medium, okay, the spring or string or whatever it is that's the column of air that's oscillating. Okay, and that helps us to get the wavelength. Okay. Questions on that one? Right, so standing wave patterns arise because identical waves travel on the spring, string, bridge, okay? And they go in opposite directions because there's new waves and reflected waves, and they keep going back and forth, okay? We call it a standing wave because the pattern is fixed, but the waves are not, okay? The pattern is fixed, but the waves are not. They keep going back and forth, okay? And causing constructive interference, destructive interference, always in the same places. Okay, that's due to the speed that they can travel, the wavelength, and the frequency. Okay, everybody good with that? Yeah? Okay. Can I induce a standing wave in something without actually physically oscillating it? Could I cause something else to resonate with something I'm doing without touching it? Okay, how? You're right, how? Yeah, having the waves, I make waves in one place, I allow the waves to travel through a medium until they hit the other object. Okay, if that object is capable of vibrating, the waves will enter that medium and cause a vibration. Okay? That's what goes on when you make sound with a wine glass. You're not actually oscillating the air. You're not going like this and making the air move. It doesn't work. Okay? But you're going around the glass. You're causing the crystal. You're making the crystal oscillate. The air is resonating with the crystal. The crystal induces that vibration in the air, and that's what we hear. It's the same with a string instrument. Okay, you pluck the string disturbs the air. Okay, it induces that vibration inside the resonance cavity of the instrument, causing the amplification of the sound. Okay, so we can induce resonance in other things. Okay, and it's important for us to realize that, because in some cases it's not something we would want. Okay, in other cases we would want to induce the vibration or resonance in something else from afar. Okay, that's kind of how radio works. Okay, you get the waves traveling from one thing to another. Okay, they cause the oscillation in the new thing, and that oscillation can then be interpreted. Did anyone ever play like telephone when they were a kid? Like the two soup cans? You guys probably had cell phones since the time a little bit. Okay, when I was a kid, we made these things with the two soup cans, right? And you could talk to your friend as long as the string was tight. And if the string's not tight, it doesn't work. Right, so what you'd do is, with the tight string, you'd talk into the tin can, and the bottom of the tin can would oscillate, and that oscillation would be transferred to the string, the wave would travel through the string, and make the can at the other end vibrate. It's the same idea if you like put a glass up against a wall or a door, and you try and listen to something going on the other side, you look creepy, right? But you're essentially, the air is hitting the door, sound travels really easily through solid objects, so it goes straight into the air that's trapped inside the glass, causes it to oscillate. You've got that right against your ear, and so that all gets transferred through. Okay? Right. Have you ever seen the spy movies where they have the spy microphones? They have like a big dish on them. Okay? There's like a microphone in the middle. Actually, they have them at like football games too. Okay? They'll have somebody standing at the side with this like curved reflector microphone. Same idea, that the waves are coming in, they're focusing them like that curved mirror thing we saw the other day. Okay, focusing them onto the microphone so that they can hear conversations. Sometimes people use that to cheat. They'll try and hear the conversations of like the coordinators, the offensive coordinator of the other team. Okay, and then in baseball they'll do the same thing. They'll pick each other's signals. Yeah, it's actually against the rules. There's like a rule about it, and you can't cheat and learn the other team's signals. So get better signals. That just seems like a good strategy. Okay. So you can induce vibration in other things. Okay, it's induced resonance, and we see it a lot. Okay, especially with sound. Okay. You know what? I think. Okay. So in this figure here, we're talking about the crests and the troughs. Why we get that? Like we get that inverted reflection. That's why we get the standing waves. So the wave comes in and reflects off the fixed end. It comes back. So at a fixed end, at the end where the reflection is always occurring, do I get a node or an antinode there? At the point the wave reflects, so at Emmanuel. Okay, Emmanuel, was the spring moving?
Huh?
Or you were holding it? Was the spring moving?
Yeah, well,
No.
it was moving me.
Yeah, well, you were holding it, right? Like, was the spring doing this, like, right in front of your face?
It was trying to.
It was trying to, but it didn't, right? You held it there, okay? Because when the wave came in, it hit him and reflected, and it created its exact opposite. So at a fixed end, you're always going to have a node, because that is the point where the reflection occurs and where the wave produces its exact opposite. The same is true at my end. There was a node right in front of the point I was oscillating, okay? Because when they're coming back, they're reflecting off of my hand. Okay? Even though I'm causing an oscillation right in front of it, there would be a node, because I'd be making a wave that was the opposite of the wave that was coming in. Okay? So I'd have a node there and then an antinode further away. Everyone all right with that? All right. Okay, so changing the length of the standing wave in an instrument obviously changes the pitch of the sound. The speed of the waves is staying the same, okay, but we're changing the wavelength. If we change the wavelength, then the string can oscillate faster, okay, like back and forth faster at a higher frequency, and produce a different sound. So if we use the full length of the guitar string, we're going to get a wavelength of what? What's the wavelength of this sound? 120 centimeters. Okay, remember, this is only half a wavelength here. Okay, so the wavelength of this sound would be 120 centimeters, and it would produce 165 hertz. Now, if I hold it here, where it's only 30 centimeters, okay, I'm going to get twice. I've reduced the wavelength, okay, by a factor of 2, so I'm going to get twice the frequency.
This could just be the diagram, but why doesn't the wavelength continue all the way to the tuning knobs?
No idea. Somebody's holding it
There's
there?
like a thing,
They're pinching it there. Yeah,
like the knob, the string that goes over the.
there's a bridge or something there, right? There's a bridge at either end?
Yes,
Yeah.
I think so.
Well, that would make sense, because otherwise, some strings would be longer than others, right? If there wasn't a.
Like the thing at the end of the thing is angled downwards.
Right, the thing at the end of the thing. I know exactly what you're talking about, because you're speaking my language, the thing at the end of the thing. Yeah, it's called a bridge. Oh, sweet, I got one right. Okay, yeah, so here, there's a bridge, okay, and that's where, like, it goes over this thing and then down to the anchoring point, okay? And then up here, there's another bridge, and it goes down over that to the tuning knobs, okay? So you've got, those are your fixed ends, is those two bridges. The vibration doesn't occur past those, but you can increase the tension of the string past that because it's connected to it, okay? So that, this bridge here was like Emmanuel, okay, on our string, and then down here is me shaking it back and forth, okay? So does that make sense? That's why it doesn't go all the way to the strings, okay? And if you're playing different notes, right, like you're pinching the string at different places, right? It's like every chord has a different shape, right? Like you pinch different strings. So some of the strings are oscillating on their full length, and other ones are not, okay? And then you got like that steel thing they put over their finger. Makes it sound different on an electric guitar. How's that look? Because you don't push it all the way down with that, right?
It's complicated.
Okay, it's complicated. I'll leave it at that. It's probably more than I'll understand. Yeah. Okay, but this is kind of the basics of it. If I change the wavelength by reducing how much of the string can vibrate, I'm going to make different frequency. I'm not changing the frequency, because I think I said that frequency can't change. But I would make new waves that have a different frequency, because these new waves have a different wavelength. Okay? Once the waves are produced, I can't change their frequency. Okay? And I can make new waves that have a different frequency. All right, we will leave it there, because the next thing is going to be about wind instruments and air columns, and I want to save that for a fresh day. So, there'll be a quiz tomorrow. It'll be like the stuff we did today with the diagrams. Okay, I'll post it later.